Hello and welcome back. We are picking up the proofs here for asymptotic notation with another proof on proving that a function f of n is not in theta of g of n. Now, to do this, it will probably be a good idea, since theta is still kind of new to us, to actually put the definition of theta down. So the definition of theta is that there exists an m1, I'm going to shorthand it here, m1 and m2 and an n naught all greater than 0, where for all n greater than n naught, m1 times g of n is going to be less than or equal to f of n, and f of n needs to be less than or equal to m2 times g of n. So we really want to bind that f of n by two different multiples of g of n. Okay, so let's now write our problems. Oh, and now we're going to show that for this example that we're not in this space. So what that means is for all m1, m2, and n naught greater than 0, there exists an n greater than n naught, where m1 times g of n needs to be greater than f of n, or f of n should be greater than, should be greater than m2 times g of n. And just like our previous question, we should be able to look at this and know that only one of these two sides is possible to be true. If m1 and m2 aren't the same value, it isn't possible for both of these sides to be true. So let's rewrite our problem in like this format here. So we have m1 times 7n² plus 1 is going to be greater than n cubed, or n cubed will be greater than m2 times fn² plus 1. Sorry, 7n² plus 1. Okay, there we go. So when we look at this, we can ask ourselves, which one of these just looks easier to prove, since both of them can't be true at the same time? Well, we're going to look at this one right here, and we're going to say, what are the chances that n² is going to be greater than n cubed? We're going to use our brains. We're going to realize that the chances are pretty low, because n² is less than n cubed and not the other way around. Now, when we look over here, n cubed is probably going to be greater than this scenario right here. That for us is something that we can probably prove to be true much easier than the other side. And since we only have to prove that one side is true, making the other side in this scenario impossible, this is the side we're going to work with. So we're going to go ahead and attempt to prove that there exists an n greater than n naught, where this is true for all of the m2s and n naughts in the world. Just rewrite this. Okay, and we see that difference in terms. And so what do we want to do? Well, we're going to do the same thing that we've done previously, which is we're going to factor out. We're going to go ahead and factor out that n², just as we've done previously. So we have m2 is factored form of this. There we go. And now we can see here that we do have a nice whole number over here. We have an addition over here. There's no reason to make our way toward a half. We might as well make our way toward a whole number if we can. So since we're trying to find an intermediary right here, if we can find an n² that we can round up on, like if we can find 1 over n² is less than 1, then we can round up if we can find an n where that works for it. Now, of course, we can see that when n equals 1, we're not able to do that round up. But if n is greater than 1, like 2 or higher, we will be able to do that. So let's just pretend for a second that our n is greater than 1. And if that's the case, we're going to be able to say n² 7 plus 1 over n². Oh, my brackets are all messed up. So this was our original. And we know that this is definitely going to be less than m2 times n² 7 plus 1. It's definitely going to be less than that. So this is our original side, and given that our n is going to be greater than 1, we know that this is definitely going to be greater. Awesome. So now we've sort of stuck that intermediary value between the n cubed and the original right-hand side. And now with that in mind, we can use this new function over here where we have n cubed greater than m2n squared 8. That's not written very nicely, but I just took this and just plopped it right there. We could now find a way to isolate our n. So if we divide both sides by m squared, we will end up with n being greater than 8m2. So we can see that as long as we define n to be bigger than 1 and also bigger than 8 times m2 for any value of m, we will be able to satisfy the right-hand side of this original statement up here. So the way we would start this proof officially would look something like this. We would say let n equal the max between here I am thinking about this just to make sure that I don't prove the wrong thing here. We want to make sure that that we're binding our values, as we said previously in previous videos, by all those for alls that are potentially affecting our n value. And so we know that we have this value right here of m2 that we're binding it by, but this other term doesn't include n naught right now. So we're not actually binding this by n naught. So what we probably want to do is say n naught plus 1 rather than just strictly greater than 1. We want to make sure that we're binding it by the for all and not criteria so that it's mathematically rigorous to say that we know that for all values of n naught, our n takes them all into consideration. So this is probably going to be an n naught and an 8m greater than, there we go, plus 1, so that we can observe that n is definitely greater than, I don't have room. N is definitely greater than the max between this n naught and 8m, like that. And that n naught, is that enough to push us up and over? Yes, it is, because if n naught is between 0 and 1, this will be bigger. And if n naught is even more giant than this term, that will work as well. Okay, so then having this information in hand allows us to say that we can observe that since n is going to be greater than n naught, we'll be able to prove this part. Oh my goodness. This part up here we'll be able to prove. And then when we observe that our n is strictly greater than 8m, we'll be able to prove this part as well. So we've broken it into our two parts as we typically do. We've inserted that intermediate value. We use the n naught to prove this side. And then that's the n naught part. And then we can use the 8m part to prove this side of it. And therefore, we'll be able to say that our original equation, which was just this side over here, held true. True or anything is just going to be true. And we're able to show that our original values are not in theta of fn squared plus 1. Okay, so that's our first sort of introduction to this not in theta example. So again, a reminder, we only have to prove one of the two sides for this OR. So don't go try to prove both sides. Turn on your brain, look at both sides, see if one side looks like it makes more sense than the other, and then start working your way through that side. With that in mind, let's go try another one. So thanks everyone for joining me, and I'll see you in the next video.